Are we starting? All right. Welcome to Tulsa Open Source Hardware. I'm your host, Jonathan Bartlett. And so here we are at, what month is this? May. Yay, it's May. Good to know. I usually don't know what month, day, or sometimes even year it is. So, start out with, Tulsa Open Source Hardware is part of Techlahoma. And we would like to thank our sponsors. First of all, we'd like to thank Project Make It for streaming and capturing. We also want to thank B&K Makerspace for providing the space for us to do this. So if you all want to come and join us live, B&K Makerspace is off of the exit ramp on the Broken Arrow Expressway on the Memorial exit, and you can go off there and find your way. The address is on the website, and you can find us that way. We encourage. There's a lot of people here who are members of B&K Makerspace, and so basically, if you're not aware, B&K Makerspace has spaces. You basically rent space monthly, and that's kind of your project space. And so you can be around a lot of makers, and there's tools available. There's people available, and you can build anything you want, basically. So anyway. We want to thank both B&K and Project Make It for making this stream and this user group possible. So as far as Techlahoma, Techlahoma is a nonprofit volunteer-run organization that puts on over 30 meetups, 2 annual conferences, and sponsors free local events. So be sure to read our code of conduct and reach out to someone on the conduct committee if you feel there's been a violation of the code of conduct. Some of our meetups cost money, so you can support Techlahoma in a variety of ways. You can go to techlahoma.org. You can find lists of all the meetups. There's a Help Wanted board, and you can support Techlahoma with Amazon Smile, a Twitch subscription, a donation, a license plate. You can ask.
We still need 80 people for the license plate to happen.
Yeah, we still need it.
Only 20 people.
So we need a lot of people to do the license plate, so we can, because we can't actually do that until we have a quorum mass of people to help us out. You can ask your company to sponsor, and you can buy something from our merch store. So anyway, so that's Techlahoma, and I hope you go to techlahoma.org to check it out. So today...
So the events that are listed are clearly out of date, but an important one coming up Friday, this Friday, is 200 OK.
200 OK.
If you haven't got a ticket, you still can.
So where's 200 OK?
200 OK will be located at the downtown library in the Greddington Center. That's the second basement floor. We still have tickets available, I believe, at 200ok.us. So go ahead and check that out. There are also a couple discounts still available for tickets if you ask. Talk around to people. You might find something. This year will not be streamed. It will be recorded, however. So if you miss it, you'll be able to catch it on YouTube in a couple days after the event. But we will not be live streaming it this year. So just a fair warning. If you were expecting to just watch the live stream, but would rather, or if you would rather, what am I trying to say? If you were expecting to be able to get away with just watching the live stream instead of having to come visit, that's not going to work this year. Please come check it out.
All right, let's see what we've got here. So we've got solve your everyday problems with genetic algorithms. APIs, the good, the bad, the ugly. Hack your brain, ways to improve your thought process. Lightning talks, my heroes are imposters too. Web localization, how to find remote roles. Data visualization isn't peripheral, it's essential. Overcoming delay, how the best devs increase productivity. Then we've got a talk on understanding iterators and iterables in JavaScript. And WTF are serverless apps. And then we'll have closing remarks and socializing and networking after that. So that's what's happening at 200 OK. So any other announcements?
I don't know of any others.
right. So today I was going to present to you all on transistors, but actually, given our makeup, you all probably know more about transistors than I do. So we'll see. We can have the game be spot the mistakes. That's kind of what the kids do in my calculus class. Is they try to find all the ways that I go wrong, which is pretty often. In fact, I have this one girl. She's in 9th grade in my calculus class, and I send her home with a test, and it's homeschool, so I just give her mom the answer key, and she gives her mom a correction to the answer key. So pretty epic. So anyway, so that's what you all can do. You can all be my you all can tell me where I'm going wrong on transistors. So anyway, so transistors are kind of the magic of electronics. A quick overview. Electronics, there's lots of different components. We've got passive components and active components. And the difference between these is passive components don't require power, and they always decrease power when you use them. Even some of them are pretty minimal decrease, but all of them, at least to some extent, decrease power. Active components, on the other hand, require an external power source and can either increase or decrease power. Because they have this external power source, they can pull in extra power as needed from their external supplies. So with passive components, what we think about are resistors. Their resistance consumes power, and so you have a voltage drop precisely because you're eating power, and they heat up and whatnot. Diodes, they soak up power to reduce voltage. Capacitors pretty much store and transfer power, but there is some loss of power. Inductors, they store and transform power. And then switches transfer power. And all these passive components, they're limited in their output options because all of the transformations must reduce the power to some extent. So it's limited in the number of things that they can do. So active components, on the other hand, have external power that they can draw from. And having a power source means that you have a greater number of transformations available than you do in your passive components. And so this allows you to boost, since you can boost the signal, you can modulate it in an unlimited number of ways. And so that's why we have computers, radios, and all those other fun things, is because we have active components that can draw from external power and boost it when necessary. So just a quick example of how amplification works is by kind of a simple precursor to the transistor, a relay. So what a relay does is, you notice down there you've got a coil and you've got a kind of a switch. So what the coil does is when you energize the coil, it'll close the switch because it'll magnetically draw the switch closed. And so what happens is you put a signal down the coil and it'll close the switch, and so you can have a bigger power supply on the switch than you had on the coil. And so you can use a small power supply to operate a switch for a larger power supply. And so that's kind of what the essence of amplification is. You use a small amount of power to control a large amount of power. So with the transistor, you have a similar action. Now there's multiple types of transistors. The ones we're going to concentrate on are called BJT NPN transistors, and we'll talk about what that means in a little bit. So there's three main parts to a transistor. You've got the collector, the emitter, and the base. So if you think about it in terms of what we were talking about with the switch, the collector to the emitter is kind of like the pathway that you have your main electricity, your heavier voltage going down, your heavier power. And then your base is a smaller amount of power that controls that gateway. Okay, so you usually connect your collector to kind of a larger power source. The emitter is the output of the transistor, and then the base controls that flow. Now, when I say the emitter is the output of the transistor, that's only kind of half true, because sometimes, even though that's where the current comes out, sometimes the signal is actually somewhere else. And we'll see how that works later on. So any questions on that? All right. So you basically have a high current flow going from the collector to the emitter, and then the base controls that flow. So there's two main classifications of transistors. You have bipolar junction transistors, BJTs, and field effect transistors. I'm more familiar with the BJTs than the FETs. So the BJTs are basically like diodes. They're constructed like diodes. They have a lot of similar properties of diodes. So the BJTs amplify current. So they primarily are for analog devices because of the current amplification. Field effect transistors amplify voltage. So we were talking about the base, the collector, and the emitter. Field effect transistors have the same ideas, but they're called different things. And there you've got the gate, the source, and the drain. And they're primarily for digital devices. They have they have less of a they're less sensitive for small amounts of variation, but they switch a lot faster. So, for example, that's why I usually use bipolars for analog signals, because they have a more continuous variation. But the field effects are faster, and they use less electricity. Actually, a lot less. So BJTs in detail. So this is a diagram of kind of the way that you should think about a transistor. So you have a diode that connects the base to the emitter. Okay, so everything that goes into the emitter comes out the collector. So, everything that goes into the base comes out of the emitter. Okay, so because there's a diode controlling that. But that diode also, you can think about it as controlling a variable resistor that's attached to the collector. And so that can be anywhere from 0 resistance to infinite resistance. And so at 0 resistance, then it's just a direct wire from the collector to the emitter. And at infinite resistance, it's as if the collector were disconnected. You usually think about the modes of operation of a transistor. There's kind of 3 modes. There's cutoff mode, which means that there is no conduction from the collector to the emitter. There's saturation mode, which means that it's just an open pipeline from the collector to the emitter. And then there's active mode. And that means that there is a proportional amount of current going from the collector to the emitter. Okay, so there's a lot of details on which one is active at which time. But basically, so as I said, there's kind of a diode that's between the base and the emitter. So if you see that VE is the voltage of the emitter. So VE plus 0.6, those are all supposed to be 0.6. I don't know why one of them says 0.5. The reason why it's VE plus 0.6 is because there's a 0.6 volt drop from the base to the emitter because of the diode. And so the base has to at least be above that cutoff point in order to open up the transistor at all. Okay, but if the base has such a high voltage that it's got more voltage than the collector, then it's all the way on, and it'll just act like an open switch or a closed switch. But in between there, if it's in active mode, what happens is that the current from the base is amplified. So if you've got, the gain of the transistor will tell you how much that's amplified. So if the gain of the transistor is 100, and you have 1 milliamp coming in the base, then that will translate to 100 milliamps coming in the collector. So that's kind of the way that the transistor works. So, there's kind of 2 ways that transistors are used. Sometimes we use transistors as a switch, kind of like that relay. And if you want to use a transistor as a switch, you usually focus on the saturation mode versus the cutoff mode. But if you want to use transistors to amplify like a sound signal or something, then you usually focus on active mode, which actually has the gain. So applications of transistors. So the one of them is in building logic gates. So you can arrange transistors in a way to do, your AND gate, your OR gate, your NOT gate, your NAND gates, all of those. So let me give you some examples of these. There it is. So here is a simple NOT gate. And so this is my input, and so it's either going to be positive or 0. Okay, so and this is my output over here. So right now I have the input is high and the output is low. Okay, and so basically what this is doing is it's taking my input and it's shorting it to ground if this is high. So it shorts all of my current to ground, but if it goes low, it turns off the transistor and allows the output to go this way. That's why I said, the emitter, even though that's where all the current goes, that's not necessarily the output. Here, the output is actually right here at the collector, and so we switch there. This gets shorted to ground, so no electricity can flow through here. If we turn it off, then the transistor goes dead, so all of the current flows through my output. So then, for another gate, that is not the right folder. So here is an AND gate. And so basically, we have our power supply here. And if we turn this off, then this transistor goes off and the rest of the circuit goes off. Okay. And if we turn it, and we can turn this one off too. But if we turn it on, then this part of the circuit turns on, but because this one isn't also on, then the rest of the circuit is off. So only when both circuits are on is there current flowing to the output. So in this case, we actually do have the output in the emitter. Okay, so that is an AND gate, and then here's an OR gate. You can do an OR gate entirely with diodes, and so a diode just makes sure that the current only flows one direction, not back the other. So now if you think about this, if this didn't have the diodes here, if we turned one on and one to ground, I would just create a short circuit. So what the diode does is it forces all the current to go this way. And so it just says if either of these are on, then I have current flowing. And if only when they're both off do I not have current flowing. So now a lot of times in electronics, what we'll do is we will combine a bunch of different transistors into a single what's called a gate. So instead of having all these detailed schematics, we'll just have one symbol for it all, like this. Okay, and I believe this is, that's a NOR gate. And there's several different gates, and so let's do one we've already done. Insert, it's your digital, so let's do an AND gate. And so the AND gate, when you see these symbols, you can assume that there's power in them, because as I said, transistors require a power source. So you can assume that all these are connected to power, but we don't always show it in the schematic. And so here, so let's turn this on. Only when both of these are on, just like our other AND gate, only when both of these are on will it conduct out the output. So so you've got AND looks like that. A more popular one, because it's more versatile, is a NAND. And so you notice the little circle on the front. That means not. So not AND. So any configuration except for AND will allow current to flow. So both of them deactivated current flows. One of them activated current flows, but when both of them are activated, current doesn't flow. So that's an AND. That's a NAND. Then ORs are kind of curved. And so that's when either of these or both of them are enabled, but not none. Okay, and so you can do NOR. Didn't want me doing them on top of each other. You can do NOR, which is not OR, so it's just like an OR, but it's got a not symbol on it. So anything that doesn't match the OR. So basically when they're both turned off, it'll allow electricity to flow. So exclusive OR means that only exactly one can be enabled. So if both of them are disabled, nothing flows. If both of them are enabled, nothing flows. Only when exactly one of them are enabled, nothing flows. So those are logic gates, and those can all be built up from smaller transistors. Then from these gates, you can build up even more stuff. In fact, you can use basic gates to build memory. So this is a 1-bit memory. Yep, it's actually, that's not the one I want to show, because that's actually more complicated. I want to start with something easier, which is none of these.
You don't have a half adder sitting around?
What?
You don't have a half adder sitting around?
No, I didn't do a half adder. Let's see here. Where did I put those? This is in. Okay. Open. There we go. 1-bit memory. There we go. So this is called an SR latch, and it stands for set and reset. So what happens with an SR latch is that you have these two sides. You've got the reset side and the set side. And so this output right now is doing nothing. But if I want to set it, I set this guy, and that sets the memory. And so this memory will stay as positive even if I turn this guy off. So this guy still has output going, and he will continue going until I tell him to reset. As soon as I tell him to reset, then he turns off. I can turn this back off, and he will still continue to be off. So set and reset, basically you set it, that's the reset. You set it, and then it stores the fact that you set it. Or then you reset it, and it stores the fact that you reset it. Okay. That's kind of confusing to use, though. So what they invented was, I believe this is called a D-latch. And so basically what happens is instead of having one switch which enables and one switch which resets, instead of having one switch that sets and one that resets, you have one that's your data signal, and the other one says whether or not we're going to store that data. So by default, if you have your enable switch turned off, it doesn't matter what your data says, it's going to do nothing. Actually, should turn this on. There we go. Let me start this over. Okay, so if I've got it disabled, it doesn't matter what I do with my data. It's not going to do anything to my output. But if I set it to enable, then the output will match whatever my data says. So if I leave my data on and then turn off the enable, then that will continue to hold that state even after I turn off my data. And you can tell that all these are done, the way these are done is through feedback loops, because notice that these actually feed back into each other. And in fact, if you compare these circuits, so the front part of these circuits is the same. Okay, so this is an SR latch that has a couple of extra circuit pieces attached to make it easier to use. Okay, So the way that this operation goes is that if you think about set and reset. So if I hit set, okay, so what's going to happen? So this brings this line high, and this is a NOR gate, okay? So that means not OR. So that means that this output line is going to be dead when it comes through here, okay? Because since this one's high, that means that because of not OR, this one's going to be low. So this one's not going to be anything coming in here. And since I'm setting and not resetting, there's nothing coming in here. So this is not OR, so this one's going to be high. And so this comes out to my output, and it also feeds back in to here. Okay, so when I turn this guy off, so this is, again, not OR. So since OR would be true, this maintains the state here. When I reset, though, then this guy goes negative, and it's also the input to this one that was remaining high. And so that's how that maintains its memory. And so these feedback loops are what allow you to maintain memory. So anyway, you can also build adders with these gates and all sorts of things all the way up to a computer. And you can actually buy chips that have just series and series of gates. So logic gates is one important aspect of transistor logics. So then you have BJT amplifiers, okay? And so there's usually 3 parts to a BJT amplifier, which kind of corresponds to the 3 terminals of the transistor itself. You have a common node that's basically connected to a standard voltage. You have a signal node, which has the input signal, and you have your output signal, which is your amplified output, okay? And so the configurations are named according to which one is attached to a power supply, whether it's positive or ground. So the most common configuration that most people get taught is called the common emitter amplifier. So since it's a common emitter, that means that the emitter is attached to a standard voltage, which in this case is ground. Okay. So this is so you connect the emitter to ground. The signal comes into the base. Now the signal always has to be greater than the emitter for the transistor to be on, if you remember from what we were talking earlier. Okay, but if you think about a signal that comes in from an audio, that's got both positive and negative voltages, right? And so the problem is that on the downswing, that voltage is going to go so low that it's going to keep the transistor off for the entire time that that's in a downswing. Okay, so what you have to do is you have to bias the signal. Okay, so you basically feed in the signal into a voltage divider that holds the voltage up, and we'll see how that looks in a second. So then the base, as that current that comes in controls the current that comes in through the collector. Okay. Now the way that you get this translated into a higher output is you put a resistor on the collector, and so the higher current through the resistor will cause what? Higher voltage, right? Because voltage is current times resistance. So if we up the current, that's going to up the voltage that's across that resistor. So you put the output right next to that resistor, and it will give you an inverted signal. And then from the output, because our voltage is now biased because of the bias input, so you couple that through a capacitor to renormalize it. So this is what it looks like. So you have your input. So on the left here, you have a voltage divider, and that maintains the voltage above the emitter state. Now there's a little resistor on the emitter, and that's somewhat ignorable. It stabilizes it. It's not really that useful to think of the resistor. But so basically you would have a capacitor on the left. That's when you have increased current coming into the transistor. When you have increased current coming into the transistor, that will increase the voltage, that will increase the current coming through the collector, which will increase the voltage across that resistor. And that will decrease the voltage on the output. And I labeled the output in the wrong place, of course. Output goes there. So the output comes out from below the resistor. And so if I have an increased current from my input, that will translate into increased voltage across that resistor next to the output, which translates to decreased voltage in the output. And likewise the reverse. So when the signal drops in current, that will decrease the current coming into the collector, which will decrease the voltage across that resistor, which will increase the voltage at the output. And so that will give you an inverted signal on the output that has an increased power. And so now, as I said, that's going to bias your output signal, so you're no longer going around 0. And so if you need to couple that to another stage of the amplifier, you can throw a capacitor in to transfer the signal basically at normalized around 0. So if you just stick a capacitor there, that will do everything you need. So, well, I guess I should. Any questions on that guy?
That's the full amp. That's not just the bias creation.
Right. The bias is the two on the left.
Okay.
So the two on the left are your voltage divider that creates a bias. For what?
To create a. Oh, I'm sorry. I'm thinking of it as just making it into positive, not creating a bias signal.
Yeah. So
You have to think like a tape deck.
so the voltage divider is what biases it. The one at the bottom right stabilizes it, and the one at the top right is what actually kind of, you can think of that as recording or translating the current changes into voltage changes. So another thing that you use transistors for a lot are outputs. And this is actually more of a terminology thing, but you'll find a lot of integrated circuits that have what are called open collector outputs. And those always baffled me for a while until I figured out what they were. And what it means is that the output actually has two states, and you usually think about an output state as either being positive or 0, right? But in this case, the two states are disconnected in 0. And so, and the way that it does that is just it has a transistor at the end, and the transistor, if it's positive, if the output should be positive, it'll have the transistor turn off, so that'll make it disconnected. And if it should be 0, they'll make the transistor turn on, which will make the collector go to ground.
You often see that when you're talking about data buses, because you don't want, if you're sending if you're trying to send data, you don't want one of them trying to drive to ground and the other one driving to voltage, because now you've got a short.
Yeah.
And if both of them are open, you might have collisions, and so by just having them both high would be collisions. So if you just have them disconnected, then the rest of the line can be driven high by, say, a pull-up resistor somewhere.
Yeah, and the other nice thing, the pull-up resistor.
Trying to get a clean off.
Right.
Yeah. The other nice thing that the pull-up resistor will do in this configuration is the chip doesn't have to decide what the output voltage will be.
Right.
Your pull-up resistor will your pull-up voltage source will decide what the output voltage is.
Although to be fair, in that situation, you still have to watch your voltages, because you can still burn out the chip when it tries to go to ground.
Yeah, they usually have a limit on how many milliamps they can drive, they can sync.
Right.
So anyway, so that is, I didn't have a lot on FETs in there because I really don't. Their operation is not. It's a little weirder, and I don't understand all the details, so I didn't really cover it that much. So
Induction, baby.
So Any questions, comments, criticisms? Did I miss something important?
Well, it's a nice start. I look forward to the part about pets.
Sounds good.
Your challenge.
My challenge will be to learn about FETs.
And obviously, as you work on this, you'll want to sip on some bubble tea. Because then, say it.
What?
Because then you can have Boba Fett.
Ah. I didn't even think about that.
That would have made a lot more sense if you called it boba tea instead of bubble tea.
Bubble Fett.
That's it. You wanna?
I think
sign
that's
us
it.
off?
Yeah. All right. Well, that was so. Let's do real quick next week, next month. So we do the third, the third Wednesday of the month. Let's see here. So that's on Meetup. Let's see here. This will create events, create a new event. Date and time. So 3rd Wednesday, and that will be our June meetup at 6 p.m. And if no one else brings anything to share, we'll have part 2 of the transistor tutorial. Focus on FETs. Even maybe Boba Fett.
Let's say fat. Maybe a little this, a little that, so it's fat-ish.
It will be fat-ish.
No, please,
no.
no. It's Declahoma.
All right.
Not okay.
Boba Fett. B&K Makerspace. There we go. Booyah! And we'll announce it later. All right. Well, I'll see y'all next month.
Yay.
Good to see y'all.
Thanks for coming.